Welcome to video 11.3 in our first Principles of Astrophotography series. In this video we offer explanations for why stars appear as pinpoints in the sky.
This video is based on section 11.3 of our first Principles of Astrophotography book, which is linked in the description below. I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensibility. Don't the lens, cornea, and vitreous humor of your eye form images on your retina in the same way that the optical system of a telescope forms images on a sensor?
Good question.
If so, then why don't bright stars appear larger than faint stars when observing visually, like they do in astrophotographs?
So, in the last few videos, we've spent trying to understand why those stars, the brighter stars, are bigger on the images, and it has to do with the stretch, and it has to do with the brightness of the stars. But why doesn't the same thing happen on your retina? When you look in the sky, and if it's been a while since you've looked up and thought about it, maybe you haven't ever thought about it when you look at the sky, but you look at the sky, and all the stars appear like pinpoints. And I did it the other night just to make sure we weren't lying, that even the bright stars look like pinpoints, and the dim stars look like pinpoints. The bright stars just appear brighter, and I think there's probably a small effect where, yeah, maybe the brighter stars form a bigger dot on your retina, but it's much less pronounced than what you see in photographs. That's the question we want to raise here.
Yeah. So principle 125. Star visual observing. When observing the sky visually, stars appear as pinpoints of light regardless of brightness. Lateral inhibition and or local retinal adaptation might explain why.
And we're grateful that I have a cousin that taught perception, particularly visual perception, at Berkeley, University of Berkeley for years. His name is Martin Banks. He put us on to this literature and helped us to understand this. We had a couple of conversations with him. So there are two things.
Lateral inhibition. When presented with a brightness gradient, the eye brightens the brighter regions and darkens the darker ones, artificially sharpening the gradient. This is cool.
So Marty pointed this out to me, that these are 6 different bands of uniform color. So this band has uniform light gray color.
So it's not brighter on the seam between the darker one and the lighter one. It is the same brightness the same way.
Exactly. And so this is a little bit darker. This whole thing right here, this whole thing is the same uniform gradient. But if you look, for example, right at this boundary here, I think if you're a normal human and not an alien, what you're going to see is that this region here appears darker, close to that boundary, and this lighter region here appears lighter, closer to that boundary. Isn't that cool?
To me, the effect is more pronounced on the lighter side. I see the brights being brighter.
Here, so maybe over here?
Yeah. Rather than the darks being darker, but it's a glass half full, half empty sort of thing.
Oh, I see. So you see that you see more of a lightening here than you see a darkening there, right? But over here, I don't see much lightening here, but I see a lot of darkening there.
Interesting. Yeah.
Okay. But the bottom line is that this is something your eye does. This isn't real. I guess you can call it an optical illusion, right? It's doing something to your field of view.
It's an optical process?
It's an optical process, yeah. It's perception. It's how your eye perceives gradients. And so what's happening here, these are called, I believe the proper pronunciation, and Marty can correct me if I'm wrong, is Mach bands, M-A-C-H, bandes de Mach. And this is a demonstration of lateral inhibition. So why might this play a role with stars? And the answer is, you got a bright star that has a profile that looks like this as a function of distance or angle from the center of the star. So there's the center, and the vertical direction is the intensity of the star. What this lateral inhibition does is this gradient right here between the bright part and the dim part of the star, it accentuates the gradient. So it's like it sharpens up the profile. It makes it seem brighter in the middle than it actually is, and darker outside than it actually is.
It's like an automatic contrast enhancer.
Yeah, I would say, yeah. So the other thing that Marty, and I was on a bike ride when Marty called me and talked to me about this other effect. We don't know what the relative amounts of these two effects are, and we haven't done any actual experiments to validate the conclusions here. But we're just offering two possible explanations to all of you so that you can have some indication of why it might be true. So the other one is local retinal adaptation.
The eye reduces the sensitivity of retinal cells that capture brighter regions of a field of view relative to the sensitivity of cells that capture fainter regions. This reminds me of a local dimming sort of thing.
Yeah. So it's a bit of a mouthful too, but I think this next figure, which we talked about in a previous video, this is the Andromeda Galaxy unstretched. And here it is stretched. Exactly the same field of view. You can see the same stars appear in both. But what we're saying with local retinal adaptation is that the retina is, the eye is an amazing instrument. And it can say, oh, this region of the Andromeda Galaxy is dimmer, so I'm going to increase my sensitivity. And then here I'm going to decrease the sensitivity. I'm going to say, oh, I don't want to think of it as so bright. So in effect, the way, and I talked to Marty about this, in effect what the eye is doing is stretching the data. The eye is automatically like stretching it.
We're pretty amazing.
Yeah. And so how that would apply to actually star sizes is that it would say that, well, here's a really bright star and here's a super dim star right here. I'm going to increase the sensitivity for that dim star.
For the dim area.
For the dim area with that dim star, so it'll appear maybe brighter than it would have been. Then I'm going to decrease the sensitivity for this bright star, trying to make them all look kind of like the same. The eye is an amazing instrument. I remember when we saw Comet Hyakutake, I think it was in the 90s, and the tail stretched 40 degrees across the sky. The best instrument for seeing that comet was not my telescope, not my binoculars, neither of which could capture the entire tail. It was my own two eyes. And I think we should all be grateful for the eyes that we have.
Yeah.
Thanks for watching.
And we'll see you next time.